the third lecture, and I suggested to give one more lecture tomorrow, so because it turns out that I wouldn't manage to come to the proof of this theory, so then now, well, I think I have more or less enough time to talk about everything, and that's fine. Yeah, so then let me start with continuing the topic which we discussed the last lecture. So, namely, it was about the so then I recall the story that we have a gamma space, so not special, not very special, so then by this we mean a function from gamma O to top with only a condition that gamma of 0 is contractible. And then you can construct B. You can restrict it to simply show there is a functor of embedding, not embedding, but function I to gamma. Then we can restrict A to delta, and this is a function from delta op to top, and then you can consider its realization. Yeah. So then actually what was called B1 or B of A, and then it was noticed that we can, for gamma space, we can, if A is not originally delta space but comes as restriction of gamma space, we can iterate this construction, namely we can use a precomposition, something like gamma O times gamma O times gamma O many times, so then we have a function from gamma O to times gamma O to from gamma, sorry, to gamma, and this makes us possible to consider firstly some iteration of this function, and then my A to top, and then restrict this one, so then I'll consider restriction. Let me denote it, but it's not really correct, by the same letter I. So then it becomes a function from delta op n times to top, and then I consider its realization. So let it be n, I don't know, n somewhere here. So let me consider this realization, and the notation for that was Bn of A. So basically the idea that using this functor we can mimic the same procedure.
And you realize along like the last, you realize along the last delta op, there's a convention.
What?
You have a bunch of delta ops. You're only taking the realization along one of them, or along, it's an iterated realization.
I don't understand. So what do you mean?
You take realization.
Yes.
Is it iterated, or you only fix one of the delta ops in
No, I iterate n, so number of copies of I apply iteration of this function.
I understand.
Yes.
So BNA is what?
It's a topological space, yes, and then as I have for any A, I have out of this condition.
You have a bunch of variables. You have a bunch of copies of delta op.
Yes, and of course.
Do you use them all up in the realization, or only use one of them?
I use one of whom? Well, I can use this realization, but it's realization of multi-simplicial topological space. It's known that it's the same that realization of the diagonal, if you like, of this, but well, doesn't matter how you regard it. The matter is that some interesting phenomena.
You're doing something different, where you had like two variables, m, comma, n. And you only use one of them to realize, and then you
this actually I did, somehow, yes, you are right. So but what I did yesterday, I wrote something like m comma n, or m times n, and then I realized it by n, say yes, in gamma, and then it would be b of A, which is again a gamma space depending on n. So this is very important that this, so this is actually somehow, in this notation, I should always write here 1. So then when I mean the term of the spectrum, I mean that I take several arguments and then compute at value 1 for the remaining 3 arguments. But in principle, it's the same stuff as saying as I said now, right? So then I take this restriction. Of course, what you mean that I can take one more copy of gamma here and it will be a free. So then I mean if I have here n copies, then I can take gamma op in power n plus 1, and then I can consider again the top in the similar fashion, and then I can actually fix, so then I can realize, so then I can restrict it to, well, I can consider delta op in power n times gamma op to top, right? Then I realize by this n simplicial arguments, and the argument, this gamma op argument is free, and then I again have gamma space again. And what was important, so then it was remarked yesterday, which I guess I said it in the first lecture, but it was to emphasize, repeat again, that if A is special, which means that A of, let me write it down in this little bit upgraded form, to AN then the times AM is homotopy equivalence, then it follows that B of A as a gamma space, again is special, so M plus N is also homotopy equivalence. So and this is, yeah, to B A of M times B A of M. Yeah, so and then the matter that if I start with a special gamma space and each gamma space, that the gamma space which then each realization bk of A is again a gamma space, right? In this way, and this is a special gamma space if original A was special, right? And this is actually quite meaning this property. And this is quite, yeah, this property is not in the first lecture, this property was formulated as A1, A to 1 in power n is homotopy equivalence, but last lecture I explained that, well, certainly this is stronger, so this implies this, but in fact they're equivalent because both of them are mapped to A1 in power m plus n, and I know, if I know that these are homotopy equivalent, this also, then I know that this is also homotopy equivalence, right? So we work with this Gurevich model structure of Rome, so then weak equivalences are just homotopy equivalence, right? So by some reason. Yeah, so then we don't work with we don't work with equivalent structure of model structure of topological spaces. Yeah, so then we last lecture we proved that actually Bn of A can be written down as what was called Sn dot over gamma some coend with A, where for any P-based topological space we associated a functor gamma to top, not gamma op, but gamma. Well, as I did it last time, so basically, so let's denote it by P dot, where P dot of n was P in power n, but there was some, well, operations which I wrote down last lecture. And then if you take P, so better to write it M probably, and if I take P equal to n-dimensional sphere and apply this construction, then I have A, which is contravariant of gamma, this one with covariant, and we have coend. And then I actually have shown that this nth term of this spectrum can be alternatively defined in this way, right? Yeah, so actually we did not talk about spectra in this way, but actually you can easily see that for any P, if you take, for example, P over gamma to any A, and take, well, the wedge product with some topological space A, then it's mapped to, this is topological space, right? And then it's mapped to, yeah, so this takes values in top, of course, right? And then it mapped to L dot P, wedge B, dot gamma A for any base topological space L, and this is actually quite clear. So if we have parameter T here and here, say P1, so on P L, and then A, and so A, L, yeah, some element like that, then we can send it just to T P1, T P2, so on, A. So then, yeah, so this is of course not in any way not some equivalence or so, but just a map. And it follows that, for example, if you have suspension of Sn gamma Sn dot gamma A, then it's mapped to Sn plus 1 dot gamma A, so then we get actually a spectrum in this way. Actually, for any spectrum P, so if we have actually P0, P1, and so on, which is a spectrum, meaning that sequence of base topological space such that delta, sigma Pi is mapped to Pi plus 1, then this same speculation gives me that I get a spectrum. In fact, I get a spectrum for any gamma space A, which I denote by Sn. So let me, by some reason, write this topological part on the right. You will see, I just rebranded, so probably I should then write gamma op or so, but I skipped it. So let me write it on the right without any change of real meaning of the notation. Yeah, so then it's again a spectrum, right? Again, a spectrum. Yeah, is it clear? So the same argument as for spheres, right? So I never used, to get a spectrum, I never used anything special except the fact that I have actually sigma Si is mapped to Si plus 1, then using, if I have the same property, so I mean I put here A equal to S1, and then I use this formula and get spectrum out of any topological spectrum P.
L is just some other point in space?
Yeah, L is some point in space, and that
this construction P dot tensor over gamma is pointed also?
Yes, it's pointed because, yeah, so we have, because A is pointed, well, A is somehow maybe weakly pointed, I don't know, well, in principle, the matter is that if from this condition, so if it was just a point, not a fat point, but just a point, that then all components and all maps of gamma would be pointed maps, because we have a unique map to 0 in the category gamma, and then this point would produce me point in any AN. But well, it's a little bit maybe subtle if you work with fat point, but basically it's about that. So let me skip this. Yeah, anyway, you get a spectrum. I guess, yeah. So then we get a spectrum, and then, at least if gamma of 0 is just a point. Yeah, and then it's quite interesting phenomenon, because we have, then we can take a product in the sense of spectrum with gamma space and get a spectrum again.
I have a question. Is there a reason why you switched the order of the factors?
Yeah, just I will explain now, because I like to write down some adjunction, and it's just decoration. It's not a serious reason, but just for some beautiful formula which I'm going to write in 5 minutes. It's better to write it down in this way, right?
But if I remember correctly, one argument is covariant and the other is contravariant.
Of gamma, but then it will be some another story. Well, okay, I will write down the following formula if you like. So let me write it down now, and then I will explain it if you prefer it in this way. Okay. So then look, if I have if X is a spectrum, which was P probably just there, it's the same dot P. Yeah, then I write down the following formula, that home in spectra of A tensor gamma x dot. X is a spectrum and x dot is this functor applied to each component of the spectrum, right? So then I guess it's quite clear, right? So I take nth term of the spectrum, apply to it the dot functor, then I, for each particular, for example, if I have xn, then I have xl in power m, and then these guys produce me a spectrum, so then I take this product, right? So then that's what is meant. Yeah, so then the formula is as follows, that if I take now the product in another spectrum, y, it's another spectrum, then it's actually the same thing as home in gamma spaces from A to, I should explain, I'm going to explain this thing, so this is another thing which is actually gamma space. Yeah. Okay. So then this is a formula, and I wrote down this p argument or x argument now on the right, just because it's more natural in the way of this formula. So what does it mean? So what is this x y? So first of all, I should recall that we have so-called, well, in principle, Sigal said these things very, somehow very naively, but I mean, more scientifically, the spectra, both model structures on spectra, strict and stable, form a simplicial model category. So then there is a simplicial home, home, which, I mean, in this simplicial sense would be a simplicial set. Like, for example, for any spectra, you have, you can take the product of any spectrum on any topological space, then you take home in spectra. So this is a spectrum, this is topological space, yes, not topological, topological space, and then y, and then you have some assignment on this, depending on this offset, which depends on topological space. So now you put k equal to delta n, the standard simplex, and in this way you get a simplicial set. And this is actually how the simplicial structure in the category of spectra is typically defined, and this actually is a simplicial model category for both model categories which people consider on spectra, but I'm not going to use it, it's just words. But actually what Sigal does, he considers it's not a simplicial set, but it's a topological space. So he likes to consider somehow not simplicial categories, but topological categories. Yeah, he doesn't like actually somehow simplicial. So by this reason, if we have, if we can a little bit think of this formula. So if you put here delta n, right, and then by n we get then some functor from delta O to sets, and this is simplicial set. And then instead we can consider something like internal home of topological space for each n, we can consider internal home of topological spaces, and there are two maps from product of over n of sigma xn to yn plus 1. Which are basically, if you have this one, so first of all, you can take xn to sigma xn to xn plus 1, and then take n plus first component on the left, and secondly, you can take sigma xn, and then you take this is fn plus 1, from here. Otherwise, you can take sigma of fn to sigma yn, and this to yn plus 1, and then you take something like equalizer in topological spaces of this diagram, and this is called, this is called xy somehow. Or maybe I call it home of x and y, so which takes values in topological space. And this is actually somehow the direct analog of this construction, but instead of considering simplicial, somehow.
But you need something more like an internal on the gamma spaces to make sense of.
Yeah, this is actually, there was some questions after the first talk that we restrict ourselves, of course, to good category of spaces for which like something like home.
No, but I mean, the thing you defined is just, is it a gamma space?
So far not, so far it's topological space.
Okay.
Yes. Yeah, so this is topological space, and let me, this is just topological space.
And it's just kind of the mapping space between the two gamma spaces.
Some like mapping space, something like analog of this simplicial home, but this he considers not simplicial but topological, but it not big difference like this. Again, there is some general fact that if you have, say, simplicial enriched category, then not simplicial model category in that sense, then you can actually apply this adjunction between simplicial sets, equivalent adjunction between simplicial sets and topological spaces with Krillin structure and get that. But actually, it would be quite messy because he doesn't consider Krillin model structure. He needs, he does it in this way. Okay. So now, here it's, as I said, here it should be gamma space. But here I have not a single spectrum, but I apply this functor dot applied to a spectrum, right? So in that sense. So basically, it means that I can define a Cartesian product of spectra. If x and y are spectra, then I define Cartesian product xy, where n term is just xn times yn. And then I define x dot as a spectrum whose nth term is is x m's, so then, it's, so how to say it, just, sorry. Anyway, anyway, what I like to say is something as follows, that I take, that I like to take, then I can apply this construction just literally, this construction P dot, I can apply not to a single topological space, but to the spectra in the same way. So as I said here, so then actually I get a spectra, I get for each term of spectrum, I get a topological space, but altogether by this formula, but altogether it comes to it is a spectrum, right? So then how to say it? That if I have a spectrum, then I have then if x is a spectrum, then I have a spectrum x dot, or I agree to write it on the right, a tensor x dot gamma. It's again a spectrum. With whose nth term, whose nth term, a gamma x n is a as topological space is x n dot gamma, which belongs to topological space. Yeah, so and then I explained that it's a Gaussian spectrum, and basically now I like to define this thing, right? So then I apply my construction P dot to its spectrum, so then I get that for a spectrum X, yes, so then I, for a spectrum X, I get a functor from gamma to spectra. Yes, so to gamma to spectra. So before I for a topological space P, I got P dot, which is a functor from gamma to topological spaces, right? Now I, instead of taking topological space, I take a spectrum, and then, the formula is something like that, that x dot n's component is just xn dot, it's, it's a spectrum whose, so that I take actually x times x times x n times, yes, n times. This is a spectrum, then I take tensor product over gamma with A, but from the other side, as I agree, right? From A, gamma, like that. So then I get something, so this guy by my formula is actually gamma object in spectra, right? So this, I mean, if I assign to n x in power n, where x is a spectrum, then I get some functor from gamma to spectra by the same formula which I had last lecture for when instead of spectra I consider topological space P. So then I can plug spectra to this formula, right? Yeah, basically, yeah. So then I get a spectrum in this way, and so then I have this, so this thing is, it's a functor. Then if I take this x, define x a tensor x n's term by this formula, then I get a spectrum. And then this is actually, so this gives me a functor from gamma to spectra. So then here important is the functoriality on n, but actually the same way how maybe I should recall you how I define the formula for this P dot, right? So, but it's basically the same. So, where it is. Let's see. I guess it's somewhere in another place. So then actually, right. So what we said is that if we have P, if we assign to n the topological space P n in A, if we assign this one where P is a base topological space, then we get a functor from gamma to topological spaces, right? And the formula was something like that, that if we have n to m, some theta, then then we have to I some subset theta of I in M, and then we should map Pn to Pm, and the formula was as follows, that so P1 Pn was mapped to x1 n, x1 xm, where xj was pi if j belongs to theta of I, and it was a base point otherwise. Yeah, so actually this construction does not use any specific topological spaces, so then I can apply it to spectra as well using the Cartesian product of spectra. Then each of this guy would be a spectrum, and then I have a map of spectra. So then it's actually, yeah, so then I get in this way, I get a functor from, yeah, so then this one is a functor from gamma to spectra out of a particular spectrum X, and then I can apply the coend construction. And then I also can apply the internal home. So then I can take this home as I defined from this spectrum X dot, which is I just defined by this formula. Yes, so again X dot, it's a functor from gamma to spectra, where n is sent to x n times. Yeah, so then I can take now this home, but for particular n, it's a spectrum, and then I can take this internal home I talked about here, this one, defined as equalizer, and this is a functor from gamma op to top. This is the idea, yeah? Because it's clear, I guess, right? So in this way I get something like right-hand side. Yeah, so well, maybe, yeah, let me denote it in this way, yeah. So at the right-hand side, yeah. So this is actually, this is actually the same, so let me use it as synonymous to x dot to y, and this is a functor from gamma op to topological spaces. Yeah, so that actually it's pretty nice junction, which is very elementary and has nothing to do with topology so far, because actually it's basically the same stuff as as we have in topological spaces for k times x, where x, k, and y are topological spaces, and then we have, of course, the formula that if we restrict ourselves to good topological spaces, it's x, y. So then basically where this is internal home, this belongs to top. So then basically I use this junction and nothing else. So then the idea is that here, so then actually the claim is that I have this isomorphism of these homes, just because, because for example here the functoriality on gamma is used in the coend, and here it's used in the home, because here I take home of gamma space, and then this coend stuff, it comes, it's transferred to this home in gamma spaces, and also I have here home in spectra, so that it's somehow sensitive to the structure map of spectra, and here the structure maps are encoded in this internal home. So anyway, I claim that this is actually very elementary. So this is just an elementary exercise on all these definitions. So then this is a junction which pretty elementary follows from this basic junction in topological spaces.
For that junction, do I need to restrict to the compactly generated?
Yes, exactly. Yes, to good spaces. Yes, and if I restrict, then I can perform in this way. Was it clear? Yeah, so then so then actually somehow, it's actually very nice, because if you now apply everything to the sphere spectrum for X,
I'm sorry if I missed it, but how is this home on the right a gamma space?
Because this x dot taken separately is a functor from gamma to spectra, as I explained. In a similar way.
Doesn't that make this home more?
Becomes, yes, of course, the home becomes functor from gamma op to some, yeah.
X.
Yeah, if you have a functor from any category C to anything, and then if you have another object y, I don't know. If you have another object y, then if you take home, say from, well, let it be x, from x, yeah, home just without any, not home in C somehow, just home to any y, that it becomes a functor from C op to anything.
Yeah, so by definition, a gamma space is a functor from gamma op.
From gamma op, yes, and I also should focus maybe on the fact that gamma of 0 is contractible. Yes. Yeah. Yeah, all homes, all topological homes are homes of base topological spaces. Yeah. So, well, this is actually the idea. Now, this is a new phenomenon. So, because this is not very interesting, I would say. But yeah. So, but let me still write it down in some maybe better way. For a particular case of sphere spectrum here, then if I take A and here I take gamma to sphere spectrum, right? Apply this construction and here any y, then I have isomorphism to form in gamma spaces from A to this home from S to Y, considered as gamma space, and let me denote this thing as R of I, meaning that it's right adjoint functor to the functor B. So this, it's known, as I explained last lecture, then this is actually B. This is a spectrum whose nth term is Bn of A. Yes, and so then this is actually that spectrum which I get after realization and the sequences of realization. And here I take a spectrum and this home takes values in functor from gamma op to top. Yeah, so then actually it's a joint. So the statement is that in this way I have a joint functors, and moreover I have it for any spectrum X instead of sphere spectrum. I have a pair of adjoint functors, but what is nice with the sphere spectrum, then this left-hand side is actually the functor B. So then I have a functor B from gamma spaces to spectra. So now, so far it's not about homotopy category of spectra, it's just on the nose. And then I have a functor R. So Sigal denotes it by A, but in my opinion there are too many A's because gamma spaces he also denote A typically. So let me denote it R as it is right adjoint. Where, yeah, so then it's from spectra to gamma spaces. Yeah, so then X is mapped to home, Y is mapped to home from sphere spectrum dot to Y. Yeah. Yeah. So now, of course, I like to have this gamma space to have nice properties. For example, if I know that I like to work with special gamma spaces at least, and so then of course this one is not a priori, well, at least when we work not homotopically, it's not a special gamma space because, for example, if I take home, that home from S times S to Y, then it has nothing to do with home from S to Y twice, so then it's totally different stuff. Yeah, so, but actually the fact which I like to use is that for any n, the embedding from the wedge product of sphere spectrum and actually for any covalent spectrum n times, yes, 2s in power n is a stable equivalence of spectra. So stable equivalence, as I said, it's a map of spectra which defines isomorphism on homotopy groups, or which I can also call stable homotopy groups. Yeah, so this is actually a fact from spectra, so it's not, I'm not going to prove it, but in any textbook of spectra you can find that for any cofibrant spectra, mean that, for example, in our setting where the structure maps are closed embeddings, then this wedge product mapped to direct product, it's a stable equivalence for Mn spectra. Stable equivalence. And this actually means that if I work with stable category, and if, maybe now I should tell something about the properties of this home, which are based on, general properties, which are basically something about the simplicial home and simplicial model categories, but these are some properties which actually are used here. So then, so the property which I'm going to use is the following, that home from X to spectra X to Y, where I have, say, X1, when I have X, say, cofibrant, meaning that just structure maps are closed invariants in this sense, and if Y1 and Y2 are fibrant, in our case it's stable model structures with modulus omega spectra, and if Y1 so X1, X2 are cofibrant, and Y and omega spectrum, then what I'm going to use is that the corresponding map of topological spaces, home X2, Y2, if I have a map F from X1 to X2, which is stable equivalence, like that map which I produced for sphere spectrum, for example, and Y is omega spectrum, then the corresponding map is homotopy equivalence of topological spaces. So this is a property which is standard. I mean that in general, if you have a model, say simplicial model category, and if it was a simplicial home taking simplicial home taking values in simplicial space, so then if X is cofibrant and you have a pair of fibrant objects and weak equivalences between them, then it produces you weak equivalence of simplicial sets, or otherwise, if Y is fibrant and you have two cofibrant X and weak equivalence between them, you have weak equivalence as well. So this is basically what we are going to use. Maybe I should write the second statement, because it also probably will be used in some place. So then if Y1 and Y2 are omega spectra, and M is X is cofibrant spectrum, and then if Y1 to Y2 is stable equivalence, then I have that home from X Y1 to home of X Y2 is homotopy equivalence of topological space, weak equivalence. Generally, in simplicial setting, it's weak equivalence of simplicial set. So, of course, I like to apply the first statement where X1, this one is X1, and this is X2. And this is stable equivalence, as I said, and of course I rely on these facts, especially also on the statement on this home, because if you're interested, you can find proofs somewhere. I think that for this spectral stuff, maybe the classical paper of Busfield-Friedlander is Boostfield Friedlander. It's actually about Siegel paper, but they construct closed model, something like bisequential, something like gamma spaces and bisequential sets and something like that. Right? Yeah, then anyway they do this, they work with gamma spaces taking values in simplicial spaces, and they do all that Siegel stuff, well, more formally, well, the ideas are less clear, but without application to what Bart is equivalent. But I think a big token of the Siegel paper they do in the language of model, closed model categories. But anyway, so let me now get some consequence from what we have. So then if I take, if I denote by spur the stable homotopy category, by which I mean that its localization of spectra, it is a whole of spectra stable, so then I mean that I localize by all stable equivalents. Or it's, well, actually I also use this fact that it's the same that homotopy category of omega spectra, but localized by strict equivalence. So by strict equivalence I mean just very naive stuff, that I have a map f0 from x0 to y0, f1 from x1 to y1, and so on, which of course commute with suspension, and such that each fi is homotopy equivalence. Yeah, this is called strict, and the fact which I also going to use, a very important fact on this spectra, that we can construct the stable category of spectra as a full subcategory of strict homotopy category of spectra, meaning that we localize by these maps. Yeah, but when we use full subcategory restricted whose objects are omega spectra. Yeah, so somehow now we go further. So let me maybe erase something written here. So then let me denote by something like SP either of this category. Yeah, so then actually if I take home in SP from my x dot to y, where y is omega spectrum, and x is cofibrant. So, for example, a sphere spectrum is a pretty nice example, which I'm going to use. Yeah, then we get actually then this one is it's pointwise. Yeah, then we have a map from here to restriction to, well, so here we are, here we associate to n home in spectra, in this stable category of spectra from x in power n to y, and we can also associate to n home in this stable category from x wedge n to y, yes, so here it's wedge product of n copies, and this is of course, this is home in spectra from x to y in power n, where power it means the product of base spaces. Yeah, and then it follows from this fact about home that the restriction map is a homotopy equivalence. Homotopy equivalence. So here I mean the following. I apply this general property, which I wish to have in simplicial model category, that if x1, x2 are cofibrant, which in our case means that the structure map of spectra are closed to embedding, then this is, and y is fibrant, which in our case means that it's omega spectrum, then we have weak equivalence in general of simplicial sets of this form. Or otherwise we have a dual statement. Yeah, well, if you look at axioms, what this simplicial closed model category is, it's actually something which Sigal interprets in this way. So basically the idea is like that we have, then if you have a model category, then you can, just model category, not simplicial, then you can, of course, compute hom, as Quillen explained, in localization and homotopy category, but if it's simplicial, then if X is cofibrant and Y is fibrant, then you can compute this, I just explained, it's not directly related, then you can compute simplicial hom from X to Y, which belongs to simplicial sets. Then you can take pi 0 from this simplicial hom. So it's a bit different procedure than you invert quasi-isomorphisms, right? Otherwise, for taking X cofibrant and Y fibrant, you use simplicial internal hom, then take pi 0, and this actually is equivalent, it's isomorphic to hom from X to Y in homotopy category. So then if you have this simplicial structure, then you get more flexibility of how you interpret the maps in homotopy category. So here we do something similar, but just we consider topological model category somehow instead of simplicial. Yeah, so anyway, we use that and we see that, well, anyway, it just wasn't just an explanation of general context, but actually what we use here, that this map is homotopy equivalent. So then the conclusion is, I should erase maybe something. Yeah, so the conclusion is that my functor R, so let me write it down here, that yeah, so the conclusion is that the functor R, this is Ry, so let Y be omega spectrum, then R of Y is special gamma space. Well, in fact, it's a very special gamma space. In fact, it is a very special gamma space, so it's a group-like. Yeah, very special gamma space. And this we can see probably, so then we compute the first component, yeah, so then this gamma space R Y on value 1, it's just hom from sphere spectrum to just in power 1 without dot to Y, and this is just Y0, right? In general. And now you need to, yeah, so this is like that, and now you need to show that it's yeah, so
what is very special? We want to show that something is group-like or
group-like, yeah, so it's
Y0 is, or Y0 is group-like or what?
This one, no, this one at value 1, so then you take the, yeah, you take pi 0 of A1, right, for gamma space A, it should be a group, right, a monoid structure, which here should be a group, and yeah, well, it should be shown somehow, I guess I prepared it, yeah, so then, yeah, okay. So, Yeah, okay, let me maybe come a bit later to this point, but yeah, anyway, what I like to say now that it's a special gamma space. For speciality of this gamma space just means that Ry from, say, n being mapped to Ry of 1 in power n, it's a homotopy equivalence. Yeah, this is speciality of my gamma space, and it follows just from this fact that it's a homotopy equivalence. So it's in stable category. Of course, yeah, if I take, maybe it's a bit wrong notation, because here I take in Hohmann spectra, but if I take yeah, then I have to take it in somehow stably, right? So that means that yeah, anyway, what I like to state finally that these considerations give me an adjunction such as, so we have to define A, which I'm going to switch now, homotopy category of gamma spaces. And the stable category of spectra, the stable homotopy category of spectra. And then we have a junction that A from B, A to, well, Y is so there is a left adjoint in spectra to A R of Y. So then yeah, so then somehow I should little bit upgrade my property for cofibrant S to, well, somehow for internal home. But yeah, anyway, yeah, so then the idea is that if Y is omega spectrum, so then if A is very special, then B A is, as we showed previously, it's connective omega spectrum, right? And if Y is omega spectrum,
am I right that this is the other way? On the right is the homotopy category of gamma space, and on the left side is S-pop.
Ah, yes, exactly, yes. Spectra, and this is A. Yes, thank you. So then if Y is omega spectrum, that Ry is very special. Somehow like that. Yes, at least special. Yeah, so then actually this is a junction, and then, yeah, well, Siegel somehow, well, does not really explain it, but because he doesn't use a model category, this model doesn't use model categories, and the way how he defined this homotopy category of gamma spaces, it's a bit tricky. So then anyway, it works to say, because, yeah, so then, actually I think that what he is doing is now, well, it's known as category of fibrant objects. So then somehow the story is as follows. So then he defines weak equivalences in gamma spaces. Weak equivalences, so then if you have A and A prime, a map of gamma spaces, F, then you call it weak equivalence. Oh yeah, weak equivalence if A1 to A prime of 1 is weak equivalence of what is the same that AN to A prime of n. If it's well, it's in principle, if it's very, well, it's not the same, but if it's special, that it's the same, right? So then it's a special case. then this is also weak equivalence. For general gamma space, not special, we should impose this relation. Yeah, and then he likes to invert, take localization by such weak equivalences. Yeah, so of course as each this map Fn is homotopy equivalence, we can invert it just on the nose, but when we invert it, then we have not a map of gamma spaces. So somehow the situation is similar to the fact that if we have a quasi-isomorphism of DG algebras, yeah, quasi-isomorphism of A1 and A2 of DG algebras, then to invert it, we have actually an A-infinity, for example, map of DG algebras, but not a map of DG algebras in the strict sense. So somehow one should think of that as quasi-isomorphism, and then we should invert it. So then anyway, this is somehow he wants to invert it in the localization category, and of course he likes to work with this stuff. So he likes to have this junction. And yeah, so then actually he uses some interesting technique which I was not aware before. Actually, I think that the name for that is the category of vibrant objects. And this is due to Kenneth Brown thesis in '73, and the thesis he wrote under supervision of Quillen. So then actually it was when model categories was just invented, and then actually the idea was something very interesting, that if you have really a model category, then for example it's something which mimics how we define, and everyone knows, a derived category of abelian category. So first of all we take homotopy category of complexes, right? Category of complexes, let me call it pre-homotopy category of complexes, and of say A, where it's abelian category, and then we look, and then the interesting fact, and then in this homotopy category, the quasi-isomorphisms, they satisfy the calculus of right fractions, right? So this is very important thing. Yeah, and this calculus of right fractions, I wrote somewhere to reproduce, so that it means, so then it's actually, the interesting thing is that such thing exists for any model category when we restrict ourselves to vibrant objects. So then the calculus of right fractions means two axioms which are found in, were invented in the book of Gabriel Zisman, that if F is any morphism and W a weak equivalence, then we can construct something like that, where this is again a weak equivalence, and the second axiom, this is the first, and the second is that if we have parallel arrows from X to Y, and if there exists V in weak equivalences such that from Y to Z, such that the compositions are equal, Y to Z are equal, then there exists some V prime from, some Z prime to X, also in weak equivalence, such that the composition from Z prime to X and then to Y are equal. So, and it turns out the meaning of these two axioms is that if they are fulfilled, then we can compute, the localization becomes more manageable, right? So, because we can compute localization by calculus of right fractions of Gabriel-Zisman. So it's not a general localization of Gabriel-Zisman, which is formed by, where forms are formed by zigzags of maps by arbitrary lengths, but we have actually, we define maps in our homotopy category as such heads, and then we say that we can compose such heads where this is omega prime, this is F prime. So just by the first axiom, we can say that it's like that and take the composition, and then actually we say that two morphisms like that are equal, W prime and F prime, where we have some other diagram where here we have also two maps in W, like that, where this where this guys is commute. Yeah, so this is actually, but yeah, this is somehow, if you have such situation, then you can at least work with such localization without even any use of model category. But what is the interesting fact of Kenneth Brown, statement of Kenneth Brown, that you can reach this situation similarly to the definition of derived category. The same phenomenon exists in any model category where each object is fibrant, or even if you restrict, for general, if you restrict on the category of fibrant objects. Namely, if you take, well, you define well, if you have x to y, then you define firstly, well, when f is homotopic to y, and this you do from the right cylinder, and then, and then it turns out that if any object is fibrant, or you restrict to fibrant full subcategory of fibrant object, then the weak equivalences satisfy in this homotopy category the calculus of right fractions, or also acyclic fibrations do. So then actually you have two ways in this setting, you have two ways of defining homotopy category in this derived category style. Namely, you can either define, so let V be weak equivalences and let Vf would be weak acyclic fibrations. So weak equivalences and fibrations. Yeah, so then you can take this, well, this, let me denote it like this pre-homotopy category when you take of your M. So then you can define of M either as V minus 1 pre of M, or similarly like Vf minus 1 pre of M, where these both guys actually satisfy these right fractions. So for me it was rather unexpected somehow, and it took time to understand what Sigal really does. But then he actually defines...
So all of this last bit is what's called Kenneth Brown's lemma.
Absolutely, there is status. No, it's not Kenneth Brown lemma. Kenneth Brown lemma does not exist. Kenneth Brown lemma as a concept in model case name, it does not exist in his status. Kenneth Brown lemma actually is due to Hovey, when he, as people say at least. But actually his thesis does not contain Kenneth Brown lemma, but contain actually very beautiful stuff. For example, somehow you can work manageably in homotopy category with this formalism. For example, what I'm going to explain now, that Sigal constructs such, well, he constructs homotopy category of gamma spaces in inverting this sort of weak equivalences. But in my opinion, he never uses any specificity of category gamma. So you can repeat the same, completely the same story for any diagram category instead of gamma. But if you want to construct really model category in equivalent sense, then you have either to assume that it's ready category, or gamma it's not ready, but gamma is what is called generalized ready. And this is a concept of Berger-Murdijk. There is a paper, generalized ready categories. So then actually, yeah, but this stuff, which I'm going to explain, you can do, I guess, for any category instead of gamma, and consider diagrams in this category and construct in manageable way. At least I cannot see really, I know, in this construction which I'm going to present, I don't see where we use anything specific for gamma. Yes, somehow it works. Okay, so let me now define finally. Yeah, so somehow actually Sigal was, I guess, aware of these ideas, and this is what he implicitly assumes, but he does not explain it in fact. But the proper model category on gamma spaces was constructed by Gustav Friedlander and using actually something like ready stuff technique. Yeah, so then what he constructs, what Sigal does, actually, he constructs. Yeah, so let me denote also this, maybe this what I call pre-homotopy category, PM. Yeah, so then he constructs.
Maurice, where are we going? Where are we going?
Yeah, we're going to this junction. So then I like to state that, well, in this category of spectra, you have B, A, and then Y, and this is well, in category of gamma. In this category A, this is stable category of spectra, and this is A, R, Y. So then I like to explain how Sigal defines this category A, the homotopy category of gamma spaces.
Okay.
He wants to invert.
So you want to explain the combinatorics of some models?
Not really combinatorics, because, well, I am not going to prove that it holds, but I just going to explain what it means, because I'm going to use it in the proof of Barrett.
So if we had done this all at the level of model categories, you would have constructed equivalent adjunction and then deduced that from the
That's correct, but it's done if you consider simplicial gamma spaces instead of topological gamma spaces, and this is done in Gospel-Friedlander, but yeah, in principle, in principle everything can be done in this way, but anyway, I can say about that there exist model categories, but in my opinion it makes sense to explain the Sigal approach, because, for example, for me it was very interesting to realize that actually it's a quite general phenomenon which he uses in his definition of category A, namely this phenomenon that you can define homotopy category of any fibrant object model category using right fractions. Yeah, so, well, basically he considers such, he uses the second way of defining it, so he considers weak equivalences and fibrations at the same time, and then he defines this stuff where you have A and here A prime, and you consider this generalized morphisms where it's W and here it's F, all are gamma spaces, where W, where for each n, A of n to A of n is Hurevich vibration with vibration, you can say, with contractible fibers. These contractible fibers. And what is actually remarkable in this story, in this definition of homotopy category, this construction, this roof to this roof, is just taking pullback. So then, for example, here taking, yeah, but it's not, well, maybe it's, yeah, okay, it should be said correctly because pullbacks do not exist here, but anyway, if you work in the initial category, you take just pullback. So then he says actually the same thing, that W is, this is a W, it's Hurevich vibration with contractible fibers, and yeah, and then these two guys are equivalent, so this is A, two primes, and these are equivalent if there is also W's and W's, such that all this compute. Yeah, and then somehow he used without any proof that that of course at first that it's correctly defined. Well, it's clear, it's known that to define such category correctly, one has to have these two axioms of Gabriel-Zisman. But for the first axiom, it's clear because if you have pullback somehow, if it's Hurevich vibration with contractible fibers, then somehow the pullback give you also vibration, and then you can, it's a general fact, and then you can see that the fibers are also contractible. But what about the second axiom? It's, in my opinion, it's absolutely not clear why they should hold in this setting, so that it's not clear. But in fact, it's general theory that it holds in such setting, and this is the theorem of Kenneth Brown. This is what I wanted to say, because, yeah, so then anyway, this now we have, so now I will state without proof two statements, that after all this stuff is defined, we have, first we have a junction, then a junction of this way, that if we are in category of spectra and take BA and here Y, then it's a stable category. That is a junction, and here it's A, and here is RY, and then here in A. And then this junction gives you equivalence of corresponding homotopy categories for A very special gamma spaces, and Y connective omega spectra. So then somehow in this way he says that we get an equivalence between very special gamma spaces, well, where localization is defined in this way, and connective omega spectra. Well, in principle, it's, well, I guess that I can, well, of course, it's maybe doesn't make sense to prove it in detail because it's quite technical, but basically it relies on two statements, at least the second one. So the first one should be proven somehow, and the second one, it's interesting. Well, at least there exists something to say, and it's, yeah, well, it's something like, yeah, that, the second, yeah, so there's two statements for the second. There are two statements, so the first is that canonical map from A to RBA is isomorphism in A if and only if A is very special. So these maps we have from the first statement, because the junction we have in general, it's like well, actually it's somehow like the Quillian pair, and this is something like Quillian equivalence, right? So he has for all gamma spaces and spectra, he has Quillian pair, and then restricted to some subcategory, he has Quillian equivalence. And then the second one is that BR of X to X is iso in S pair if X is connective omega spectra.
Is in general this composition BR just a truncation?
Once again, please.
Oh, well, I think you can truncate a spectrum to get a connective spectrum, right?
What he's asking is, suppose X is not connective, it's a general spectrum.
Yes.
You apply this functor, first R, then B. You get a new spectrum with a map to X. Is it the connective cover of X?
But this replacement does not preserve stable homotopy type, right?
Well, I don't know,
Because
resolve first, that's a kind of technical.
yeah, then the answer is not. So then, but you can, yeah.
No, but
Huh?
you didn't answer the question.
No.
You're answering some technicality.
Yes.
So if X is a nice spectrum, so that these functors R and B behave well,
Yes.
and I apply it, does it compute the connected cover of X? Is it just the truncation in the T structure on spectra? And I think the answer must be yes. So
No, but
I think the answer must be yes by one. I mean.
no, but you have invariant stable homotopy groups. Your replacement should preserve stable homotopy groups.
Come on.
No.
This is not.
Okay, maybe the answer that I
He's
don't
asking
know.
a moral question. You're answering a technical
Yes.
question.
Okay. Yes. Anyway, yeah. So this is actually this state. This is. Yeah, so this is a statement actually which he uses, and morally it's about that, for example, if you work with operatic sense, then this, in operatic technique, then we have then we have EN algebras in topological spaces which are group-like. So it means that topological spaces X on which operand En acts, and then on pi 0 of X we get the corresponding structure on groups on one side. On another side we have n-1 connected spaces y. And then we have here, we have this functors, which is also denoted by b, which is constructed by bn, say, by May, and here we have functor omega n, nth loop space. And then, in principle, in May paper or book, iterated loop spaces, it's written that we get an equivalence of homotopy categories and this stuff, and then for n equal infinity, we get here some group-like infinity algebra, group-like, and here we have connective omega spectra. Connective omega spectra. And then actually what Sigal does, it's actually some another way of establishing this equivalence when instead of E-infinity algebras we use gamma spaces. And then he shows that in this form one can easily deduce this theorem of Barrett-Pretty-Quillen, well, quite easily. So, but of course the price is that we should really carefully prove these statements, but as soon as we have proven that, we can really get everything. So then, maybe so I'm going to talk about this in the next lecture, but let me maybe start with now, so then, and I repeat a little bit next time. So then, so then actually the natural way of getting gamma spaces are categories. So then actually we have definition which is gamma category. And then there is a source of getting this gamma category. So then it's a category, it's a functor from gamma up to cat, small categories where x, where c of 0 it's just a point, one object category, and so he defines it really as with this speciality condition, and then n plus m to c of n times c of m is equivalence of category, just equivalence of categories. And then he says, then actually it follows that if he applies the nerve functor to a category, so then Cn, we can apply the nerve functor of Cn, which is a classical, which is simplicial set, which it was to recall, and then we have the realization Cn, then this is called B. Cn, Bcn, yes, it's a category, particular category for n. And then it turns out that the assignment from n to Bcn is gamma space, special gamma space. Yeah, so well, it's actually, we can obtain it quite automatically, and I'm going maybe to explain it in the beginning of the next lecture. Well, maybe I should recall what the nerve is, right? Because maybe this I'm going to use anyway, and then of course to recall, because not everyone. So let me let me recall that we have that hominoid M. I have defined xm, which was a simplicial set, right? Yeah, so monoid can be regarded as a category with a single object, and morphism from this object to itself are this M, set M. So then we can we can actually generalize this construction easily. Namely, C can be a category, and then we can define its nerve as a simplicial set in the following way. So then its nth term is a product over n plus 1 objects. Here we have just a single object. This is why this is dropped in C. And here we have such chains of maps from x0 to some f1 to x1, so on to xn, fn. So then, taking it formally, it's just the product from home x0, x1 times home x0, xn minus 1, xn. So the claim is that this assignment gives you a simplicial set. Yeah, and then there is a smart way to explain it. So how we can see, well, we can of course mimic the same formulas as we did for the monoid case, namely two extreme maps, just factor, project along the first and the last factor, and for not extreme phase maps, we take the composition. But there is a smarter way to explain it, and this smarter way is some interpretation of the category data.
Is gamma category like a symmetric monoidal category?
Not really, yeah, well, in principle, yes, but not precisely, because, yeah, so then what Sigal does, he takes, morally, he takes any symmetric monoidal.
The answer is yes.
No, the answer is, yeah, it's not yes, because, yes, well, for any, out of any symmetric monoidal category, we can construct gamma category. Out of any category with direct sums, we can construct gamma category. But to say that it's yes, literally, it's not correct.
Well, it's a homotopy coherent version of a symmetric monoidal category.
Yes, yes, okay. Yeah, so, but, yeah, so then, yeah, so the...
You're misleading the youth.
What?
You're misleading the youth.
Use of what?
Youth.
Use. Oh, okay. So then, you can actually consider IN. This is very nice category, which is poset of all of n objects, right? 3 to n. This is called IN. And then very simple fact is that fact 1 that cat functors from IN to IM, it's exactly delta from n to m. So this you can see, so mean that you have a map of categories, so then it should somehow respect the order, and then you can see immediately that it's like that. And fact 2, that n of c k, it's exactly a functor, so then from homes in cat from ik to c. Yes? So then what I have written here, the chains of, say, k morphism, composable morphism, can be alternatively defined as a functor from the standard category to C. So from this perspective, one can easily see that it's actually a simplicial set, because if you have a function, say map from n to m in delta, right, then it gives me equivalently from the fact 1 a functor from in to im, and then I can precompose. So if I have im to c, this is an element of nerve of cm, then I can precompose. So if it's phi, this I denote also phi. So from in to im, then I get this functor, which is an element of my nerve of cm. So this is actually not m. This is very nice because we immediately see without any explicit formulas, in particular this our case or even this more general case. Yeah, so then probably it's time to stop because my time is over. So then, yeah, so then this is the definition. We can of course define it explicitly. So then in the similar way that d0 of this chain of f1, fn is just f2, f3, so on, fn. Then all intermediate ones, di for I greater than 0, less than n, fn, it's just fi plus 1, so I take the product and the rest is unchanged. And dn is the projection of f0, f1, fn, it's just f1, fn minus 1. But so then you can also define the action of degeneracy maps by plugging units. But this is some explicit formula. But this is a very nice interpretation of this formula. Yeah, so then it's time to stop. So next lecture we start with this proving that this construction produces from gamma category gamma space, and next we see that we get some gamma category from any category with direct sums. And then in particular we will formulate and show how to prove this theory. Yeah, well, I'm sorry for that part of my talk, which is homotopical part. Well, I guess that it was quite messy, but actually it was less messy than what is written in Sigala. In particular, I was quite happy to find that what he really uses for this definition of category A, the homotopy category of gamma cat, is actually the construction of Kenneth Brown, and I really like this construction very much because, for example, I can construct in this way homotopy category of any category of diagrams, I guess, without any problem. So in a manageable way, so I don't need ready assumption. So then it's, I mean, it's less restrictive. So the idea is that actually what Kenneth Brown did, he firstly formulated this theorem on the model categories, and then he says that, okay, now we can take only that part of model, closed model category structure, which he uses in this construction. And then he talks only on weak equivalence and fibrations, and then there are some axioms which he can formulate without reference to any reference to co-fibrations. And then he proves that theorem, that it's localization, that it's right fraction, yeah, in this setting. And then actually, so then you can somehow, you can work with, you know, yeah, so then somehow he managed to, I guess, to define this stuff in much more examples than Quillen model structure. For example, the category of diagrams. I mean, if you like to do it combinatorially.
You still have next.
Yes.
Yeah, I realized that.
No, I just say that I think that I understand that this part was quite messy, but I really did my best to explain something, but I'm not sure that I can really explain it. Otherwise, I can use some formula.
But it's only in the next lecture that something interesting.
Yeah, okay, let's make the speaker first.
Yeah, sorry.
Any questions? Chris, you want?
Just a comment that
Yes.
nothing has happened yet. All of the content will be in the last lecture.
So far.
Yeah.
Yeah, well, it's something about gamma spaces and this.
Okay, I mean,
Well, I don't think that it's nothing.
Okay, let's keep the suspense.
Yeah, well, I don't know why you say that. I don't know so well. I mean, that nothing related to quantum equivalence theorem, that's correct.
yeah,
But it's not nothing.
okay.
It's some setting for that. So that we can prove it.
Okay, let us thank the speaker. And we'll resume.